Okay, so welcome back, everybody. So last time, I think the last discussion uh, that we had was concerning an Athenian mathematician by the name of Antiphon. Kind of a nice canonical way to see how Athenian math kind of progressed. Is to consider how they approached the problem of finding the area of a circle, right? Right, computing the area of a circle. Of course, we know that if you got a circle of some radius, um, then the area is, pi r squared. So we know this formula well. Um, so how did the Greeks approach? What was an early approach to actually showing this, right? So you might have seen some hand wavy type approaches here. So intuitively, kind of the approach that you might see in like an elementary school classroom is the following: consider a circular disc that I've drawn like this, say a pizza, right? And slice this pizza into a great number of slices. You can arrange half of those slices with the point pointing up and the other halves pointing down. And the result that you get if you do this, right? This is kind of the intuitive idea. The result you get here, well, that's it's a terrible drawing. The result you get from doing that looks like this kind of. So we'll say that we've done it with like 4 pieces. Okay, here, here's my rearranged circle. Okay, and it looks something like this. Now, the more and more pieces you cut this thing into, the flatter this edge gets, right? Until if you've cut this into smaller and smaller and smaller pieces, then ultimately what you get is roughly a parallelogram. And the height of that parallelogram is easy to compute. It's just r. Okay, so then you have to make an argument about the other dimension being pi r to be able to actually compute this thing. And all of this, this is hand wavy, and as you can see already, this idea of splitting this circle into more and more pieces is heading towards that Zeno's paradox problem of the Greeks didn't have a notion of limit, so any kind of method that used this, there was something to be worked out there. So, of course, there were, and we are going to talk about Greeks using a method of exhaustion. In fact, what I'm about to, talk about is an example of the Greeks using a method of exhaustion in this way. But this required a little bit too much hand waving to see. So then, as I mentioned last time, the idea that Antiphon had was to consider inscribed regular polygons. So, in particular, to consider inscribed regular 2 to the n-gons. Okay, and so here's an example of like an inscribed regular octagon. Okay, and there were bounds that you could put on. So you knew that an inscribed square, a regular four-gon or 2 squared gon, takes up more than 1/2 the area of a circle. The inscribed octagon takes up more than 3/4 the area of the circle. And another bound that they knew was that an inscribed 2 to the n-gon takes up more than 1 minus 1 over 2 to the n minus 1 of the area of the circle. And so this is that method of exhaustion bit that I mentioned before. So yeah, an inscribed regular 2 to the n-gon takes up more than 1 minus 1 over 2 to the n minus 1 of the area of the circle. And this was first done in Euclid's, or so this was written out for the first time, like explicitly in Euclid's Elements. But this was something that was basically begun by Antiphon. Okay, this was the idea. And as I mentioned last time, the goal here was eventually, when you had some really, really big inscribed, so see, you can barely even see the difference between this polygon and the circle itself. When you have some really big 2 to the n-gon, the idea is to look at opposite vertices on this polygon and connect them. Well, when you do that, what do you get? You get a diameter. Okay, you get a diameter of the circle. And it was known that the area of a regular 2 to the n-gon is equal, or I should say not equal, is proportional to the square on its diameter. Right, so diameter we define for a circle, but the diameter of a regular 2 to the n-gon, is this connecting opposite vertices, right? So if we connect opposite vertices, we get diameter of circle. So the idea is to have some really, really big 2 to the n-gon that's inscribed inside a circle. So it's taking up almost all of the area, right? By this fact that was written down later, it takes up all but 1 minus 1 over 2 to the n minus 1, whatever fraction that is. It takes up all of that, so minus a tiny, tiny bit of the area of the circle. Okay, and then we know this fact that the area of a regular 2 to the n-gon is proportional to the square on its diameter, and so as this area, this 2 to the n-gon, takes up more and more and more of the circle, it's almost all of the area of the circle. And since it's proportional to the square on its diameter, that means the area of the circle is proportional to the square on its diameter. Now, okay. Okay. All right. So this was basically this was the end, right? When you get to this step, then you understand that, oh, well, this proportionality constant in fact needs to be, you know exactly what it needs to be to figure out that this area formula is pi r squared. Okay. So this is the idea, and so this was kind of the central thing that led to discovering the formula for the area of the circle. And so this was done. This was completed by Eudoxus, who we'll mention later. But this was completed by Eudoxus, begun by Antiphon. Okay. All right. So Antiphon was working around 425 BC. Okay. So this method of exhaustion used in this way. So the method of exhaustion specifically is computing the area of some region involving a curve by exhausting the area with things that you know how to compute the area of. So exhausting, imagine computing the area underneath a curve by computing areas of rectangles, right? So I specifically mentioned that example to tie that in with how integral calculus is done, right? So when we introduce the Riemann sum to compute the area under a curve, the definition of a definite integral, right, that we give is defined in terms of limits, right? That so, when we discuss integral calculus, we want to compute, say, the area under this curve. And in order to do that, right, we compute the sum of, so whether we're doing lower, upper sums, right, left, midpoint sums, whatever thing we're doing. Let's say we're doing left sums here. Okay, so in order to compute this area, what is actually computed are the area of 4 rectangles, right? So rectangle 1, 2, 3, and 4. And so those areas are summed. And the idea is that that gives an approximation to the entire area underneath this curve. And of course, if I refine this over and over and over again so that I'm doing more and more and more rectangles, then I'm getting a more accurate approximation. And then, of course, everything there is still finite, right? So even if I split it into 10 million rectangles, it might not be something that I can hand draw, but that's something, that I could still consider, and it would be an extremely close approximation, okay, but it still would not be the actual area under the curve. In order to compute the exact area under the curve, I would need to pass to a limit, okay, which of course, came much, much later, and the Greeks had no concept of this. So this argument was known as the method of exhaustion, and it turns out that they did, however, anticipate a lot of this, and one in particular later, around 200-ish BC, had Archimedes. Archimedes came extremely close to essentially developing a technique that is almost integration. Okay, it is almost computing Riemann sums in a really, really ingenious way. So, and we'll talk a lot about that. So, this is something that was hinted at by the Greeks, and they were comfortable with like some basic arguments like this. But again, it was a strictly finite thing. In fact, Antiphon, you might say, well, wait, like how were they able to stay strictly finite when they're clearly trying to make some limiting argument here? Antiphon actually claimed that the circle was a regular polygon. So to Antiphon, the circle was a regular polygon. It's just it had so many sides we couldn't perceive it. So the idea here was that there was some smallest side length, okay, and once you had specified that, the circular was a regular polygon having that many, having that side length as its side, and over again copied however many times it took. So very much in the spirit of Zeno, or questions that Zeno raised, he was a finitist, right? He thought that the circle actually was a type of polygon in this way. So anyway, that was the contribution of Antiphon. There's a mathematician known as Hippocrates, not to be confused with the physician, so not the physician. All right, not the person responsible for the Hippocratic Oath. So this was around 430 BC. So supposedly Hippocrates came to Athens from Chios, so of Chios, which was another Greek island near present-day Turkey. And so he apparently came to Athens at about 430 BC because he had been bamboozled in some business prospect. So someone had scammed him, and he came to Athens to have it legally settled. And while he was waiting for that to be worked out, he basically took up learning geometry as a side hustle and selling his lessons, basically charging people to teach geometry, and he used that time and money to study philosophy and more geometry. So that's what Hippocrates did. So actually his material, so he's responsible, not in the writing, but his material ultimately is what was compiled by Euclid, responsible for books, I believe books 3 and 4. So books 3 and 4 of the Elements. He is also responsible for something that you might not even realize that you've been using all this time. So he was the first to refer to exponents or exponentiation as dynamos, which you might recognize is the Greek word meaning power. So the phrase raising x to the fifth power, the reason why in English we use the word power is due to Hippocrates, because in Greek he used the word dynamos, which means power. Okay. So that's a little subtle thing that has affected all of us. He may have been the first to use the method of proof known as reductio ad absurdum, or proof by contradiction. So reduction to the absurd, right? So you begin by making an assumption and you show that it leads to an absurd conclusion. If you followed the rules of logic, the only possible issue there is that initial assumption is wrong. All right, so we used this to prove that the square root of 2 was irrational. So he may have been the first to use that, although that's not conclusive, but he may have been the first to use this method of proof. He was the first, so his big contribution is, well, I won't say it's his biggest. He had two big contributions. So he was the first to precisely compute the region, or the area of a region bounded by curves that were not lines, actually, I should say, I was going to say we're not lines or circles, but I believe he's the first to do this period, so that were not lines. So what I mean by this is consider the following picture. So I was going to draw this, but I think it's better if I show you the picture. Okay, so consider this picture. Okay, we begin with the semicircle on the segment AB. Okay, so we have semicircle on the segment AB. Now, by the theorem of Thales, or I guess the converse of the theorem of Thales, we can choose this C, right? So this point C here makes this triangle in question a right triangle. Okay, so I have point C here on this semicircle, makes this ABC triangle a right triangle. What does that mean? How does that help us? Well, because it's a right triangle, by the Theorem of Pythagoras, I know that the sum of the squares AC side length squared and BC side length squared is equal to AB squared. Okay, so that's just by the Pythagorean theorem, because AB is the hypotenuse of this right triangle. Okay, now I also know that since that earlier fact from Antiphon shows that the circle is proportional to the square on its diameter, well, then the semicircle being having one half the area of the circle is also proportional to the square on its diameter. Okay, but also these semicircles, these semicircles in question, are also proportional to the side, or to the square on their diameter. Okay, but I know that AC squared plus BC squared is equal to AB squared. Okay. Notice that there's overlap here between all of these semicircles. If I were to subtract off the overlap, what I have left are what this picture is calling the lune. So there's the lune AC, which is this crescent shape. That's why it's called lune, for the crescent moon. So there's this crescent shape AC and this crescent shape BC. And I want to compute the area of the sum of those two crescent moons. Well, how can I do that? Since I know that AC squared plus BC squared is equal to AB squared, and since I know that this large semicircle is proportional to the square on its diameter, and so are these smaller semicircles proportional to the squares on their diameter, what I know is that if I subtract off this overlap, the area I'm left with is the area of the triangle. But I know how to compute the area of the triangle. So the sum of the area of the lune of AC and the lune CB, that sum has to be equal to the area of the triangle. And so, going back here, so area of lune AC in that picture plus the area of lune BC, this is equal to area of the triangle ABC. But I know how to compute that. That's just 1/2 BC times AB. Or sorry, BC times AC, not AB. AB is the hypotenuse. Okay. And so this is a very precise formula that computes exactly that, the area of that region, right? So this, unlike the slight hand waving that had to be done in the previous argument by exhaustion, none of that needs to be done here. Those areas are literally equal, right? Going back here. So getting rid of the smaller areas, I'm left with the sum of the area of these two lunes. And that is equal to the area of this right triangle. Okay. So that's a neat little trick that Hippocrates used. So the other big contribution Hippocrates is known for is his doubling of the cube. Also contributed to doubling the cube. So he was able to show some sufficient conditions for doubling the cube, but he wasn't able to construct the quantities in a way that satisfied Plato, and so the doubling the cube remained something that was not solved. So to remind you, the problem of doubling the cube is I give you a cube, and you are tasked with constructing a cube that has exactly double its volume. Okay. And so the question is, what was wrong with Hippocrates' approach? As before, Plato didn't like it because it did not stick to using just lines and circles. Okay, so it did not stick to using just compass and straight edge. And so this doubling the cube is sometimes known as the Delian problem. The reason it's known as the Delian problem is supposedly this issue of doubling the cube was brought to the oracle at Delos. Okay, and the oracle responded that, well, if you want to understand doubling the cube, I should rephrase this. So basically, the doubling the cube problem was originally supposedly framed not being brought to the oracle for help with it. It was actually framed as the oracle posing it to the Athenians. And so the way that this story goes is Athenians needed help during a plague. So this was 430 BC. So the Athenians needed help during a plague, and they consulted the oracle of Delos for help. and the oracle basically told them to double a marble altar. Okay, so there was an altar of Apollo that was roughly a cube, and they were told to double it, okay, in size, meaning in volume. Okay, and when the plague did not stop after their attempts to do this, the oracle explained that the Athenians, trying to double the cube, had only doubled the edges, right, which does not actually double the altar. Okay, so they had doubled the edges, but that doesn't double its volume. Okay, so the Athenians were not able to do this, but apparently the plague went away on its own anyway. So I guess, I guess it's okay. I guess it worked out all right. But that's the reason why it's called the Delium problem, because this was supposedly how it was framed, or how it came about. So Hippocrates showed that if we could find quantities x and y such that 1 over x is x over y, and that's y over 2, then x cubed is equal to 2. Okay, and so beginning, with so basically, this would allow you to construct the cubed root of 2, which is exactly the thing you need to do in order to double the cube. Okay, and so the problem of doubling the cube is really the problem of constructing the cubed root of 2. Okay. So whether or not Hippocrates is actually able to do this using these quantities is not known, but this is what is known is that it didn't satisfy Plato. It didn't satisfy this restriction to only use compass and straight edge, because as I've already spilled the beans, it's actually impossible to do this with compass and straight edge. Okay, so of course, now I could mention Socrates and Plato themselves. So I won't speak too much on the philosophical contributions because that would take far too long. But so Socrates was Plato's mentor. So Plato is a student of Socrates. And Socrates had a belief, at least Plato's dialogues, indicate that he had a belief in math being recalled knowledge, right? It is like just a matter of remembering. So people don't necessarily learn math or geometry, they just remember it. There's some kind of access to primeval knowledge well that just you already have access to. You just need to remember, right? This massive store of cosmic knowledge or something. This is one interpretation of it, that all of these things are merely remembered. And there's a few examples in Plato's dialogues of this being illustrated. So there's an example of Socrates literally grabbing random people on the street and basically teaching them rudimentary geometry, or leading them through rudimentary geometry to show that anyone, and of course in the Athenians' day, the stratification of society was you would have had plenty of people that were literally illiterate, unable to read, but the point was that they could still be taught these geometric facts because they had some kind of inherent a priori knowledge of geometry. And so this definitely was so Plato certainly shared this kind of this kind of belief. So Plato himself lived from 429 to 349 BC. And after Socrates' death, Plato traveled to Heliopolis, which is now near Cairo. So he traveled to Heliopolis and to Cyrene in Libya, and he studied there with Theodorus. Theodorus had proven the irrationality of square roots of non-square integers less than 18. This would actually be completed entirely by a later student of Plato's. After this, Plato went to Italy, where he studied with Archytas, who was the head of the Pythagorean school. And this is Archytas was someone who had doubled the cube. But again, the methods that he used to do so were not just compass and straight edge, so probably not too impressive to Plato. By the time Plato returned to Athens around 380 BC, so Plato studied in Egypt and Libya before returning to Athens in 380 BC and founding the academy. All right, the famous legendary academy of Plato. And above the door of the academy was the inscription, "Let no one ignorant of geometry enter here." Okay. So what was the purpose of this inscription? What was meant to be passed on here? Was it really just that, Plato loved geometry so much that he just wanted to be surrounded by people who were good at geometry, and he didn't want to, rub elbows with the plebs that didn't know anything about geometry? It's mostly that Plato believed that these quantities, and we'll talk more about this later, but these things of study, geometry, numbers, math in general, were absolute and perfect, in that they were immaterial, right? So they didn't exist in the same way that the chair you're sitting in exists, or a cup, right, exists. But they still had some existence, and their existence was independent of human experience. So to Plato, this question of, is math, created or discovered, right? Is it invented or discovered? For Plato, it was obvious that it was discovered. These quantities are things that existed completely independently of human thought and experience, and that studying them, because they are absolute and perfect, is the thing that would bring basically inherent goodness and morality to humans, because it was basically the only way to illuminate the good path. And so basically, studying geometry and mathematics is viewed by Plato as being kind of like the path to righteousness, due to it would definitely confer some special knowledge on you that would allow you to be a more moral person. This is kind of central to Plato's beliefs about it. And I'll talk a little bit more about that in a bit. And as I've mentioned previously, for all of Plato's love of math and geometry, he didn't really have any individual contributions. There's not a single theorem of Plato or anything. His big contribution is the insistence on compass and straight edge solutions as the proper solutions to those classical problems. And last time we saw this quadratrix, right, of Hippias, and that is an ingenious construction, and it would be very, in fact, I'm not actually sure exactly what is known about how many things can be constructed with that. There would still be some things that you wouldn't be able to construct with it, but you could construct more. You could square the circle, you could trisect an angle, and maybe not with the quadratrix itself, but with other curves similar to it, you can double the cube. But this insistence of compass and straight edge constructions, it's not totally out of nowhere. When you study the more advanced math that comes later that actually shows what goes wrong, the part where it goes wrong is exactly what you butt up against with compass and straight edge constructions. So there really was something that, Plato had a point basically when he supposedly included this restriction. That the only proper solutions be compass and straight edge constructions to these. The other thing that I've already mentioned before is the Pythagorean solids, right, are more commonly known as the Platonic solids because they're discussed at length in the Timaeus. And so more frequently you'll hear people talk about the Platonic solids rather than saying regular polyhedra or the Pythagorean solids, even though they were considered by the Pythagoreans prior to Plato. So that's another way that Plato had kind of muscled in because it was something that had been discussed at length in his dialogues. So Plato had a student. It's kind of the last contribution before moving on, and then I'll return to Plato and discussions of Plato and Aristotle briefly, and that way you can experience my disdain for Aristotle. And I am definitely Team Plato all the way. I don't like Aristotle very much. So Plato had a student, Thaetetus. Yeah, I'm not an Aristotle fan. Sorry for any Aristotle lovers. It's just, I have my reasons. I just don't like him. So Thaetetus was a student of Plato's. He died in battle in 369 BC. And he had Plato dedicated a dialogue to him. And he showed that the square root of a natural number, that is a positive integer, the square root of a natural number is irrational if and only if it is not a square. So this is a big advancement. One of Plato's mentors, one of the people Plato studied with in Libya, was responsible for showing this fact for every non-square integer less than 18. So this student of Plato's actually completed that for every non-square integer. So take a positive non-square integer. It is irrational if it's not a square. Okay. And so this shows that since squares are relatively rare among the natural numbers, there's a ton of these, right? There's a ton of these irrational numbers. So it wasn't just that square root of 2 is irrational and maybe there's a few more here and there. No, there's plenty of these, right? Okay. So supposedly Thaetetus is responsible for the material in books 10 and 13. In the Elements. all these attributions, the one that's the most rock solid is the attribution to Eudoxus of Book 5. All of the others are passed through many centuries of claims that are not necessarily verifiable. So it's hard to it is hard to nail down exactly where these sources came from. And so there have been a lot of historians that don't basically attribute. So the material itself in the elements, and we'll discuss this plenty, but the material itself, almost none of it is original, but all of the proofs are Euclid's own, I believe. So I believe that almost all of the proofs in the elements are Euclid's, and not passed on, which is why they tend to be slicker than the previous proofs of these facts. Okay, so the most important Athenian mathematician of all is Eudoxus, and he's arguably the most important Greek mathematician prior to Euclid. And in terms of ability, he's probably the most impressive prior to Archimedes, who's kind of like the king of ancient mathematicians. So Eudoxus of Canitis. Okay, lived from 408 to 355 BC. He studied with Plato. For years. He actually he studied in Plato's academy. He walked there. He commuted on foot from the harbor district. So he commuted to Plato's academy. On foot from the harbor district. He studied astronomy, medicine, geography, philosophy, but mathematics is what he's known for. He also had studied in Heliopolis, just like Plato. He had also studied with Archytas, except Plato studied with Archytas in Libya. He studied with Archytas in Tarentum, which is a city in southern Italy. And anyway, he actually disagreed with some of Plato's philosophy. Eudoxus was an Epicurean before Epicureans were cool. So he agreed with Epicurus that basically hedonism was the way, maximizing pleasure, minimizing pain. And so the main thing that Eudoxus is responsible for, I've already mentioned some of the things that he did, so he was responsible for finishing this proof that the area of a circle is proportional to the square on its diameter. So this was something that Eudoxus finished the proof of, begun by Antiphon. One of the things he's most famous for is the theory of proportion. So the reason why this is important is this is the entire contents of Book 5 of the Elements. In fact, if I break out my copy of the Elements, so let's go here. So Book 5. These diagrams are the same as the original diagrams. So you see a lot of lines here. Broken into, you can't see it maybe at that zoom ratio. Let me bring it forward a little bit. So here's Book 5, where first things defined are parts, multiples, have a ratio, to be in the same ratio, have a greater ratio, to be proportionate. All these are definitions of these things. Okay. If you look here, you'll notice all these segments broken into different pieces. The thing that is going on here is a bunch of propositions nailing down, look at this, nailing down the number system. And the way that that is done is with the theory of proportion. Now, as I mentioned before, the reason why this is such a big deal is that it's hard for us to imagine doing algebra without the real numbers. We are taught from a young age to make use of them even before we actually understand what's the difference between, say, a real number and, some finite decimal. Or like a generic real number, I mean. So we have experience, of course, from a young age with infinite repeating decimals, right? 1/3, 2/3, these things. But we still make use of the real numbers in ways that we maybe don't always think about. So what is the idea that Eudoxus, or what is it that he was wanting to do? So let's say I want to come up with a way of comparing proportions. So A over B and C over D, right? How can I say, for instance, that A over B and C over D are equal? How would you go about doing this? Well, in fact, from the very first time you algebraically had to deal with fractions, you were told immediately, the first thing you learned is to cross multiply. You were told that this was true if and only if A times D was equal to B times C, right? And so this was the key defining principle of equal fractions, because it was a problem. The fact that you could have multiple fractions that were each equal to the same thing, that's a problem. But Eudoxus doesn't have access to this. Why not? Because of this multiplication that has to occur. There is a weakness, okay? There's a weakness geometrically here. Okay, and that's all of these applications are being applied to geometry, right? That was the thing. And so the issue here is that AD and BC, these products, might not make sense to the Greeks. How so? What if A and B are measurements of an arc of a circle, right? So A is a measurement of an arc of a circle, B is a measurement of another arc of a circle, and I want to consider the ratio. Well, that ratio makes sense. And then say that C and D are angle measurements, right? So C is some angle measurement, D is some angle measurement. That ratio makes sense, right? It makes sense to say that a 30-degree angle is 1/3 of a 90-degree angle, right? And so it makes sense to talk about the proportion of a 30-degree angle to a 90-degree angle. Okay. So what does it mean for those two ratios to be equal, or to be able to compare those? If we tried to use this, what would I get? I would get the length of an arc of a circle times an angle is equal to the length of an arc of a circle times some other angle? It doesn't make sense to multiply the length of an arc of some curve with an angle, right? That multiplication wouldn't make sense. Okay, so we use multiplication algebraically to define these proportions. Eudoxus actually wanted to do it in the opposite direction. He used the proportions to define multiplication. So he couldn't do this even if he wanted to, because it would have been circular. Okay, he wanted to do the opposite thing. He wants to use proportion to define multiplication. And so let's say we have the proportion A is to B as C is to D. So we would write that in this way. Okay, so A is to B as C is to D. This is what we would write instead of A over B is equal to C over D. That way we don't sully our equal sign. Okay. So we would write it like this, and of course we would say that this was true if and only if AD is equal to BC. But we don't have access to this. Okay, so this is no good. I can't do that. All right, and so how did Eudoxus deal with this? So the definition he used is that A is to B as C is to D if and only if for all positive integers P and Q, PA is greater than QB if and only if PC is greater than QD. And PA is less than QB if and only if PC is less than QD. Okay. What does this mean for us? So if we take A over B and C over D to be positive real numbers, so if we take these both to be positive reals, then this means that the set of rationals above A over B is equal to the set of rationals above C over D. And secondly, the set of rationals below A over B is equal to the set of rationals below C over D. Okay. This is very close to how we define real numbers today. This is very, very close. So you may not have ever seen the explicit construction of real numbers. It's important because it's the basis of, all of the, if you're doing computations and they live in the reals, then those real numbers are the basis for those computations, right? So this is very close to the modern construction of the reals, due to Dedekind. The technique, or the quantity that was used here, are called Dedekind cuts. It's named after a person. So the construction of the reals by Dedekind cuts is the classic construction of the reals. This wasn't done until the late 1800s, early 1900s. Let me see when this was done. Richard Dedekind. He's German, so it would have been Ricard, I guess. So let's see here. Where's his construction of the reals? Late 1800s, yeah, late 1800s. It's like in the 1880s. Yep. So this was done in the late 1880s. Okay. So it might seem crazy that it took that long for there to be like a really, really rigorous treatment of this stuff. But a lot of these things in foundational math was kind of treated as obvious. And it turns out that it's just not the case. Without this rigorous treatment, there are many, many pitfalls. There's lots of contradictions that abound. So I'm going to talk a little bit more about Eudoxus, and then I'll move on. I will quickly go over next time compass and straight edge constructions. I won't go through the proof that those things are impossible. I'll just show you why. I'll show you the reasoning that shows why those things are impossible, and then I'll move on to discussing Euclid. So we've been mentioning Euclid periodically throughout the course. So finally, we will talk about Euclid and the holy elements. So I'll do that on Wednesday. I may assign some homework today or tomorrow, like your next homework set, which will be like 2-ish questions that will basically 2 to 3 questions from some of the stuff we've done since speaking about the Babylonians. So anyway, I think that's it for today. So I will see you all on Wednesday. Let me know if you have any questions before then. I'll try to respond as quickly as I can. So see you all on Wednesday.